In this video, we're going to think about the principle of superposition. We said in the last video that in order for us to analyze these complex structures, we made use of two key principles. One was the principle of superposition and one was the principle of virtual work. I'm going to focus just on the principle of superposition in this particular video. What we will cover is going to be really key to you understanding everything that follows thereafter. So take your time with this video, stop it, pause it, watch it again and again until you're happy with what we've discussed in this video. So let's get stuck in. We're going to start off, like we always do, with considering a simple structure, right? A simple version of a complex structure. Okay, I know that sounds a bit ridiculous, but a simple version of one. So let's think about the simplest type of structure we can come up with. So let's start off with a cantilever. And I'm going to give it some thickness here. Just to indicate that that's going to be a member that will experience some bending. Now, so far, that's just a regular structure. To make it a compound structure, we need to add something to it. So if I'm looking at this as an engineer, the obvious thing I want to do is I want to provide some support over to that right-hand side to stop it dipping down. What I'll do is I'll say, let's put some kind of a tie on that right-hand end like so. Any engineer looking at that cantilever will want to do the very same thing. You'll want to somehow support or prop up that end. What we now have is a complex or a compound structure. Let's just label it up. Okay, we have a pin. So that circle there I've just drawn in, that's just to indicate that that's a pin. And let's just say we've got some load on it here, which we'll call P. Some labels here. This is our cantilever, and this is our axially loaded tie. Okay, so we look at that and we think, okay, well, hang on a second. That's 3 reactions potentially at A, and you've drawn a pin at C, and that's potentially 2 reactions. So that would make 5. We've got 3 equations of statics, and so that would mean it's statically indeterminate to 2 degrees. But actually, that's not the case. The fact that we have a tie at C means that there's only going to be a vertical reaction force generated at C. Okay, so there's no horizontal force coming onto the structure, and it's a vertical tie between C and D. And so the only force that can be applied at C is a vertical force downwards along the line of that tie. And so that means you're never going to have a horizontal reaction at C, and for that reason, there are 4 unknown reactions in this case, and so it's statically indeterminate to 1 degree. Let's just make a quick note of that. So the first step in trying to unpick this structure and analysing this structure is thinking about it in terms of superposition. So what we really want to do is we want to cut the structure back. So we use this term cut back to reproduce the same effect or the same result as that structure by using 2 statically determinate structures. So let that sink in for a second. What have I just said? We're going to look at that statically indeterminate structure and we're going to say, right, I want to replace that by superimposing 2 statically determinate structures, and statically determinate structures are easier to analyse. So that's going to bring us on a little bit. There's a structure. That is the same as, that's equivalent, structurally equivalent to, that's the best way to think of it actually. It's not the same as, but it's structurally equivalent to the following 2 structures, or the superposition or the combination of the following 2 structures. So we've got a regular cantilever first of all, and then added to that we have, let's not forget the fact that P is on there. So we've got our regular cantilever here with our external load applied, and we're going to refer to that as the cutback structure because we've taken the complex structure and we've cut it back, we've reduced it in some way to make a simple or a simpler statically determinate structure. So that's going to be the cutback structure, and that's always what you're going to end up doing. You're going to look at your compound structure and the first question you're going to ask yourself is, right, what can I do to cut this structure back, to simplify it, to make it a statically determinate structure? That's not the end of the story because we've cut it back, but we have to somehow reproduce the same effect structurally as the compound structure. So we need to add something to it. So we add to it the effect that we have taken away. So we took away a tie force at the end. So we need to add a structure to our cutback structure which reintroduces that tie force at the end. And that's going to be called a reactant structure. So we start off with our complex structure on the left-hand side, and if you look at that and you look at what we said it was equivalent to a simpler cut-back structure, which was just a cantilever, statically determinate, plus some other cantilever structure where we've reapplied the force that we took away. So we took away the tie force to produce our cutback structure, and then we need to add that back in, okay, to produce the same structural effect. We need to add that force back in, and that's our reactant structure where we've added the force back in. So now what we have is two different, well, they're the same type of structure, but they're both statically determinate. The cutback structure is simply a cantilever with a point load P at the midspan, and the reactant structure is simply another cantilever structure with a reaction force applied at the tip of the cantilever. So another way to think about this would actually be, you don't necessarily, you can forget about him for a second. That's really what you have. You've got a force applied back in on the right hand side, which replaces the tie force you took out in order to create the cutback structure. So we now just have two statically determinate cantilevers. So where does that leave us? How does that move things along for us? Well, if we think about it, we can analyse the cutback structure. So far, I can analyse the cutback structure because that's just a simple cantilever. Now I don't know or, so I can't analyse the reactant structure yet. How do I go and analyse that reactant structure? That's the sticking point now. Well, the answer to that is we're going to break that reactant structure up one more time. So let's look at our reactant structure. Now that is the same as a structure. Bear with me, this is going to appear a little bit odd to start off with. I'll just draw it out first and then I'll explain it. That reactant structure is the same as the same structure, right? But instead of applying some unknown force or on the end, I'm going to apply a 1 kilonewton force, okay? And I'm just going to scale that force by some factor alpha, right? So this is going to make sense in a minute. I've taken or and I've replaced it. I've got rid of or. That's no use to me. I don't know what or is. I can't do anything with that. But I've replaced it with a 1 kilonewton force and some scaling factor. So you take your 1 kilonewton, you multiply it by some unknown scale factor alpha, and you get or. Okay, you might be thinking to yourself, you know, you haven't really helped me out here. You've just taken one unknown or and replaced it with another unknown alpha. But there is a method to this. Let's take this structure. Okay. So we know we can apply 1 kilonewton on the end here. 1 kilonewton. Now, all of a sudden, that becomes a structure we can analyse because all that is a cantilever with an upward force of 1 kilonewton on the end. We're going to take that, which I can deal with, I can analyse that, and somehow we multiply it by some scaling factor alpha. Right, so let's see where we are so far. Let's summarise progress. We have a cutback structure. That was this guy right here. Okay, so we have a cutback structure, simple cantilever, with our external load applied. That gives us a set of forces and moments. Okay, so we can say that would give us a set of moments, which we'll designate as M0. And in this case, it doesn't, but potentially in a different structure, it could give us a set of forces, which we would designate as P0. Okay, so these are the associated forces and moments. So forces and moments associated with that structure. So that was a cutback structure. We then had a reactant structure, and that reactant structure was subsequently broken down into a unit structure, and we can analyze that also. So that has a set of moments and forces, which we would designate as M1 and P1. So these are just placeholder designations at this stage, but these are associated forces and moments. Remember, I'm able to analyze that, and I'm able to analyze that, and we have this unknown scale factor, alpha, and that is unknown, right? That's the big question now at this stage. So this whole complex structure is going to be unlocked by working out what alpha is. So that's what the problem boils down to. So we could say, just to summarize, the problem boils down to finding alpha. What is alpha? In this case, remember, alpha was just some scaling factor, some factor multiplied by 1 kilonewton. So what alpha actually is the tie force in that very original structure. Okay, alpha is actually going to be the tie force in here, because we said that original structure was the same as the cutback structure plus the reactant structure. The reactant structure was just the structure with the force that I had taken away reapplied with the designation or. We then divided that structure into a structure where we replaced or with 1 kilonewton times alpha. Now 1 kilonewton is just 1 kilonewton. That means that alpha is actually the unknown force in the tie. And once you have the unknown force in the tie, you have unlocked the whole thing, and it becomes a very straightforward question to consider. So a summary of the situation is The moments in the very original structure that we started to try and analyse are going to be equal to our M0 moments, which are the moments in the cutback structure, plus some scaling factor alpha times our M1 moments. Now, those are the moments in the structure that just had the unit load applied. And we have any potential axial forces in that structure are simply equal to P0, the forces associated with the cutback structure, plus the scaling factor, the unknown scaling factor alpha, times P1, which would be the forces in the unit structure. So let's label these up. This is what we're trying to find. This we can analyse easily. This we can analyse easily. So that just leaves the unknown factor alpha. And we're going to use the principle of virtual work to calculate alpha. So that's where the principle of virtual work comes in. Okay, so in the next video, we're going to work out how I actually apply the principle of virtual work to find alpha. And as I say, once we find alpha, we've unlocked the entire structure and it becomes a very, very straightforward process in completing the analysis for that whole complex structure.